So welcome everybody, and it's our pleasure to start today our next trimester of the SEED seminar on random geometry and quantum gravity. And let me also thank our sponsor, Fondation Mathématique Jacques Adamar, l'Institut Poincaré, the Institut de Mathématiques Guitter, University Paris Saclay, le CNRS en mathématiques, l'École d'ingénieurs La Rochelle et les centres physique théorique. And today we are also in the new building of Institut Poincaré, in particular in the room dedicated to Yvonne Choquet-Broard, who recently passed away. And so let me now introduce our speaker. The first speaker of today is Bertrand Duplantier, and he's going to tell us about the Hamiltonian path of random planar maps. Thank you.
Thank you. Thank you very much. I would like to thank the organizers for the invitation and experimenting this nice room, especially with Zoom. So I'm going to speak about some work done with Philippe Francesco for the first paper, and Olivier Golinelli and Emmanuel Guitter, all of them at Saclay, in the Institute for Theoretical Physics, IPHT. And so these are two papers in physics, nuclear physics. Of course, there's nothing nuclear here, but they kept the title because it's a very famous journal. They wanted to change it at some point because nuclear was no longer in fashion, but they realized that they could not. So anyway, that's why you find most papers in field theory or normalization, gauge theories and so on. Anyway, we could have put the second paper in CMP, I think, because this one, it was, essentially at the level of rigorous. The first one, as you will see, is more exploratory. And so let me go on. So I will start with something simple, which is you take a line, you put two endpoints, you put them black and white alternatively, and you try to join the black and the white by arches, non-crossing arches, and above and below the line. And so you have two endpoints, so it's finite system. You call Z to the end the number of different ways, so it's a partition function if you want. And so this is a problem which was looked at originally by Guitter, Christiansen, and Nielsen in 1999. So it looks like simple, but actually it's not solved up to now. And there is, as usual, there is an Ansatz, which is that this number, when n is large, should grow like some exponential factor, so mu to the 2n. Then there is a correction, which is a power law, and to the 2 minus gamma in the denominator. And then you have, of course, some coefficient chi, which would correspond to that particular problem. But it's a purely combinatorial problem. And so from enumeration data, you get a value for mu square, which is 10 essentially, and then a value for gamma with some error bars. And there was a conjecture made in 99 by these people, which is gamma would be given by some square root of 13. You will see later where it comes from, and some generalizations of this. And so which corresponds to the value observed. So if you look at the numbers here, n is up to 34. These are the latest ones. The numbers are huge. It's bigger than Avogadro's number. They are really enormous numbers. Figures. So we are going to address this problem in a very indirect way. We are going to use B's, the honeycomb lattice. So you take the honeycomb lattice, and so I'm going to make a huge detour, as you will see. It's typical of theoretical physics. But of course, you are welcome to solve the problem yourself, right? Starting tonight on your copybook. So you define what is a fully packed loop model, FPL, of n. N will be the fugacity, the weight associated to each loop. So you fill your lattice. This is the lattice. So actually, in the calculations we made, we were on a sphere. So you won't see the sphere here, but think about the sphere topology. And you fill your lattice, and you fill it with loops, and you leave no vertex unvisited. So loops run on the edges of the honeycomb lattice, and which visit all the vertices of the lattice. and with a weight n per loop. So this is just the ON model, but fully packed. So it's a special bicubic lattice, cubic because all vertices have degree 3, and bicubic because actually there is a normal alternate coloring in black and white, as you did with the honeycomb. And then you make it a bit disordered. Your B is drunk a bit too much, and you start by disordering the lattice. So the random version to the right, the random bicubic planar map. So what happens that all the faces of your map now have even degrees, even number of faces, right? Before it was 6, now it's just an even number. So it's a quantum gravity in the parlance of physics, quantum gravity version. And so we on the left, we had the FPL model on the honeycomb lattice. Now we have it on the random bicubic planar map. Sorry about these things. We worked a lot to make them disappear, but to no avail. Okay, so now take your random planar map on a sphere filled with this fully packed. Well, actually, in that case, we took only one loop. And by the way, so I should say two things here. First of all, you take the n equals 0 limit of your ON model or fully packed model, and in that case, you wait more and more, you make all the loops disappear except for one. Of course, if you take n equals 1, your partition function will be 1 or something like that. But if you take the n equals 0 limit, there is the factor n, there is a first term in n, and the coefficient of the n is the partition function of the single loop filling the lattice. That's a trick originally due to Dejean, 72. He understood that in the sport. He was doing sports in the Alps. In the winter at Christmas, he realized that the ON model, and when n goes to 0, was providing single loops or single chains, so indeed polymers. He understood that. He realized that the calculation by Ken Wilson, this American physicist, they did calculation to third order in epsilon. Epsilon was 4 minus d, the dimension of space. He realized that if you take n equals 0, you still have exponents which are non-trivial. He realized it was polymer exponents. He rushed back to Paris and wrote his paper. His paper was half of his Nobel Prize in 91. N equals 0 limit due to the key thing. And of course, it had many followers up. And so anyway, so now you have n equals, you take n equals n going to 0 first, and then you look at your random planar map filled with one loop, and you cut the loop, and you stretch everything, and you get exactly what is underneath. So the original problem we had, the combinatorial problem, is nothing but the problem of Hamiltonian cycle on a random bicubic map. Well, then we have tools. By the way, before I turn to the problem, remember it was bicubic, so it means alternate black and white. The arches are joining black and white only. But if you look at the problem of just arches for non-bicolored line, then it's actually easy to calculate. This is the last two lines. It's just given by a product of Catalan numbers with some commutator factor, which actually is a product of 2 cat n cat of n plus 1. And then it scales like 4 to the 2n divided by n to the 3. So this is just pure combinatorics, easy to do. And if you look at what is on the top two lines, this corresponds with what we did with Kostov a long time ago to illustrate the KP-Z relation at the time, which I'm going to turn to in a minute. So that is partition function. So with a little z of n with a dot, with a O means the non-bicolor. So you can show in the let's say with the field theory project should be some power mu to the 2n, and then this gamma naught is given by the gamma of the central charge -2. I will come to the central charge later, which corresponds to -1, which is exactly what you get from the point. So it's something we knew at the time already. So the dense phase corresponds to the dense phase of the polymers. But the fully packed is different. It's different in the following way. Oh, by the way, before I go to the following way, I have to introduce sorry, I jumped a bit ahead. The KP-Z relation, which I'm going to use in a savage way today. So what are the KPZ relations? So it dates back from 88, so Knizhnik-Polyakov-Zamolodchikov. Then there was a version by DDK, means David Disler-Kawai. It was a bit simpler to understand. And then there were proofs after that, one starting with Scott Sheffield. And so what are the, so you have to, I don't know about you, I mean, if people here have done, mostly combinatorics, you are probably not very familiar with these things. But, and when I say, field theory, conformal field theory, central charge, maybe some people don't know what it is exactly, but essentially this is kind of, if you think about the Ising model, you think about the spins. When you're looking from far away, they look like the magnetization, the local looks like a field. And the central charge for the Ising model is one half. So you have a lot of things which are known. Central charge is some parameter which labels which theory, which critical system you have. Percolation is equal 0. Ising model is equal 1/2. Spanning tree is equal -2. Dense polymer is equal -2. Potts model, Q4 Potts model is equal 1. That's the maximal C we have here in this theory. And you see this maximal C because you have this famous formula, the first one due to KPZ, which labels this gamma exponent. You see on the top, you have the partition function of your system. So you look at so of course, this is a continuum version of the random planar maps. But the idea is that if you take a random planar map, as I wrote on the top, of fixed area A, the partition function will scale like mu to the A, this kind of growth, exponential growth, which we are not very interested in. And then the correction, which is A to the gamma minus 3. So before we had the factor 2 because there was an extra factor n for the point where you cut. So anyway, so you have this formula coming from field theory. And this formula relates gamma to C, the central charge. And actually, clearly, central charge is going to be less than 1. And or greater than 25. But in our case, it will be less than 1. And so you have, this is the first prediction of this approach. And the second prediction is when you look at correlation functions of operators. So people call them operators. Actually, they are just insertions of field powers, say. And we call them operators. They have nothing to do with operators in algebra. And so there are fields. They are labeled by two things: the conformal weight h sub I for the field phi I, and then the central charge. And they have conformal weight hi. Then it means that correlation function of the two fields at a distance r is going to decay like 1 over r to the 4 hi. Okay? So this is what you have in the non-random setting. So when you are in the plane. So for instance, it would be the correlation function of two spins in the Ising model, which decay with the distance with some factor with certain hi. I here means just the field you look, the index of the field you look at. And then the prediction of KPZ is that if you take a correlation function, it would be good to have a laser, but correlation function product of the phi, product of the I of phi sub hi and C, then this correlation function, unnormalized meaning you multiply it by the partition function. When you take an expectation, it should be divided by the function. That correlation is going to unnormalize, is going to scale like mu to the A, like the partition function. And then it will be a correction, which is exactly the same as before, gamma C minus 3 to the right. But then you have the sum of all the insertions, I, of 1. Why 1? Because your insertion is going to be any place on your random surface. Okay, so you have a factor A because you put the insertion at any place. You don't know where you are. You always sum of the possibilities. And then you have a decay of the correlation function with a factor minus delta, which is exponent minus delta. So that exponent minus delta is called the scaling exponent in quantum gravity. So it is the delta of HIC, just the image in quantum gravity of your exponent HI. And the formula is given by this famous KPZ formula here, this one. So of course it's square root, but of course it means that HI is the quadratic form of delta. So this is a fundamental one. So you see you put H here, and that's it. The rest is C. So here it is 1 minus C to the right. and you get your delta. So this is a prediction of KPZ, which we could derive with Scott, for instance, within the framework of Liouville quantum gravity, with essentially the exponential of the Gaussian free field as a random measure. So that was a prediction. And so in principle, if you know H, you know delta. If you know delta, you know H. So that's something we will use for the Hamiltonian path. So I go back to the fully packed model before using KPZ. So you remember you on the left. So this on the top, you have the list of people who work on this model, this fully packed model in the mid-90s. There was a lot of activity when people realized that there was something special about the fully packed condition compared to the being dense in the one model. And what is special is the fact that you have this. So U here, U is a weight you put to each vertex which occupied the edge. Okay. So when U goes to infinity, it means you enforce the fully packed condition. So U going to infinity is just fully packed. And so it corresponds to U minus 1 going to 0. So this is a line. This is a line which would be good to have a stick. Of course, not in the. No, that's okay. I think it's noticed. They don't have anything. Anyway, so this is this line here. I don't have, no, I don't, I can't do that. No, because it's not, no, that's okay. Anyway, so the line is just the horizontal line. You have n, which is between 0 and 2 in our case. And then you have, on the top, you have on the top line, up to this point where you have the divergent arrows. This is a dilute one model. So this is a line of fixed points, of critical points of the dilute one. And the branch which goes after this, this virage here, you just go back and you have this dense one which is stable. So it means that you are attracted by the dense. And there is this unstable line which is U going to infinity, U minus 2 equals 0. Okay. So the fully packed is just the horizontal line which is clearly unstable. And so it's a special one with different exponents. That was a whole observation of these people. So just a motivation. And now I'm going to go to the description of the fully packed model in field theory by the Coulomb gas. So that was understood somehow. So there were a lot of work at that time. I was not so much aware of these works at that time. I was doing something else. So they, Bleuter and Linus in particular, so they showed, first of all, that the central charge, we are going to see central charge later, central charge of the dense one is actually shifted by 1 to get the fully packed one, because there is an extra free field appearing, which you will see in a few minutes. So now you want to understand exactly why there is this shift. So you are going to, I'm going to give you a short description of the system on the lattice. So you are in the plane. You are not in the random setting, just in the plane. So in the hexagonal lattice. So you fill all your edges like on this cartoon, but you orient your lines. So now you make a correspondence with weights A, B, C on the edges. And the correspondence will be such that when you cross an edge, so when you cross from black to white and you cross to the top, you put plus A, plus B, plus C, okay, with this convention. And then if you think in terms of the occupied arrows, I mean, red arrows corresponds exactly what happens here. A when you have nothing, B when you have an arrow from black to white, and C when you go from white to black. But if you make a full turn around the black edge here and the black dot here at the middle, so you have X plus B plus C plus A. So, and you return, so it means A plus B plus C should be equal to 0. So it will be typically represented by vectors into space with A plus B plus C equals 0. Okay, so that's somehow the root of the studies which are in the mid-90s. So they are complex, they are quite rich, But if you have no A, it means, suppose you have here a defect. You see, you have a defect because here there are three edges which are not covered. Okay, so there's one side which has not been visited, so that's a defect of the fully packed condition to the left here. So when you do that, you turn from x plus A plus 2A plus 3A. So it means in that case, you should have, we may have to, yeah, but
just
really?
Just.
Oh, merci. Okay. Merci bien. Okay, so here you have a defect, this is not visited, so plus A plus 2A plus 3A. So A should be equal to 0. In that case, you will have B plus C equals 0. So it will be one component height. So, and this is exactly the description. So you take this set of vectors here, A plus B plus C equals 0. So you define B2, which is B minus C, 0, 1. So you have a nice Cartesian coordinates. And then you define A like this, B like this, C like this. And then you are going to define, you say that your height in your system, when you look from far away, your height, your system of heights, which is calculated the way I showed before, should be decomposed on two vectors, A and B, like A and B2 here, with some components which are coefficients, which are pure numbers, psi1 and psi2. And then you say, so this is what people argued for, that your fields psi1 and psi2 are going essentially ruled by Gaussian free fields. So CG here in this stands for Coulomb gas. And it will be, as usual, the interval over your physical space, a subcoupling constant G, and then the gradients of the size. There is 1/3 here because of this normalization. And then there are some extra couplings linked with what is called the charge at infinity, E naught, and then the curvature if you have on a cylinder. And psi2 is going to be coupled. So I'm not going to explain this, but you have to understand that somehow the intuition of this, the details, how to fix the constant is kind of tricky, but I'm going to give you the answers. And essentially, of course, there is a kind of crystallography here. So there is a certain repeat lattice, where if you change your height by this combination of vectors, you are going to find the same local configuration of your height. So it means there is everything is this psi is just this combination is R squared modulo the repeat lattice. Anyway, you have a free field theory, and you have two fields. One we associate with A, psi1, very important. One associated with B2, psi2. And this part here looks like what you have normally in the Coulomb gas of the ON model. So the difference between the fully packed model and the ON model is the occurrence of this A term, psi1. Yes? G is what is called the coupling constant. I'm going to fix it as a function of n, the number of components of your ON model, or FPL of n model. Okay? G will be 1/2 for the fully packed Hamiltonian path. Hamiltonian means the single path filling all the lattice. So actually, this is just this slide. It's fixed by this formula here. In terms of, so you have seen that for people who look at SLE, you know there is a correspondence between G of kappa and N in terms of the ON model. And actually, for people like SLE beta, kappa is, in terms of G, is just 4 over G. That's the kappa of the SLE kappa representation of the ON model. Here, this is exactly the same parameterization as for the ON model. And for the dense phase, we are in between 1/2 and 1, and for N between 0 and 2. In our case, N equals 0, so it corresponds G equals 1/2 for the Hamiltonian case. Okay. And then the E naught we had before is fixed in terms of G. And again, so this is the same representation as before. And the fact that you have two fields, but that the fact that this one is actually the same as the ON model. So this is the dense ON model. So this is central charge of the model. But you have an extra field here, which is free. So it's an extra degree of freedom. So central charge jumps by +1. And that is the formula we all know since the age of Nienhuis in the mid-80s. The correspondence between central charge and the coupling constant, which is correspond. Of course, if you put 1 here and take this formula here, the formula here with kappa, you find the usual central charge of the SLE kappa. But without the +1, so 1 minus 6 and so on. Okay, that's the usual formula. So actually, that's the next slide. If you jump the difference from dense to fully packed, is that if you do dense, you cancel the A component, you cancel psi1, and you have the repeat lattice is just the integer numbers, and then you have 1 minus 6 and that formula with kappa equal 4 over G. It's just, as I said, the central charge of the SLE kappa. Schramm-Loewner Evolution. Okay, so it's clear what is new in the fully packed, this extra degree of freedom A. Okay? And we saw when there was a defect that A was going to be equal to 0 locally. Okay, so what we did then in this study, and that's where the surprise came in, that we decided to look not only at gamma, this exponent, with the square root of 13, but correlation functions of defects. And so we started to look at defects at a distance R. Okay, so you will have a defect which we call a defect will be a certain jump of height, which is locally enforced by a defect, a geometrical defect. So the jump of height would be delta x, which we call m because it's like magnetization in the Coulomb gas approach. And of course, if you have a defect, you have an anti-defect minus m at the other extremity. And then we have this nice formula, which comes from the Coulomb gas. So this is just a standard formula for the dense phase with psi2. And then there is an extra one for the psi1 component. So you have to admit this. This is something you get from the Coulomb gas approach, developed by physicists in the mid-80s. We reconsidered in the mid-90s by the other people, in particular Condev, De Gier, and Inois, in 96. So you see, it means, you remember these H are the conformal weights in the plane. Remember, I call it H, these are the H's which are in the KPZ formula. Okay. So these ones, you are going to be able to put them in the KPZ formula, but you know how to compute them because you have this Coulomb gas. Of course, by the way, people who are doing SLE, many of these Coulomb gas formulae, not this one, but the other ones, have been recalculated with a pure SLE argument. All of these multiple line exponents exist in the SLE kappa case, and they correspond to the formula, with G being 4 over kappa. So what I'm saying here is that you have these two parts. One is psi1. Psi1, remember, is the coefficient of the A term, A vector, and phi2 is the coefficient of the B2. And so this is the general formula for G. In our case, n equals 0. We want the Hamiltonian path problem. Remember, we started with this. So n is equal to 0, so G equals 1/2, and this is our formula. So it means if you know phi1, if you know phi2, you have this exponent which you calculate. You have this extra term, except if phi2 is equal to 0. Okay. And then we say, yes, indeed, that's a good question. I will return to that in the very last slide. So good anticipation. So yes, in principle, but it's supposed to be universal. It's supposed not to depend on the lattice in the scaling limit. Right? When you do SLE, you're already in the continuum. But thank you for the question. Good question. And so I give you examples. So for instance, if you take one, you want to have the correlation function with open edges. So you cut, instead of having a single loop, you cut and you want to open with a line. You want to have an open line. So if you want to take an open line, well, if you locally, you will have this starting here, finishing here. So locally, if you take a turn, you will see two A's, the empty edges, two A's, and one B. So 2A plus B, remember? So it means in that case, which you can rewrite, of course, because B2 was B minus C, you can write 3/2 and 1/2. So this phi1 will be 3/2, phi2 will be 1/2. Phi1, phi2 will be essentially just, just number, okay? Just fractional number. And and then if you calculate, you take the formula we had before, you calculate it, with the one I had here, you put 3/2, 1/2, calculate it for n equals 0, of course. you find 0. So weight 0. Yeah. So in delta will also be 0. So it means if you take an open line, these h's are just 0 for the Hamiltonian path. Take now something else. You want to put a loop in the middle of other loops. So you put a single loop in the middle of it. In that case, you will have a defect A plus B plus B. Okay, A plus 2B. This is actually B2. So in that case, you just have phi1 equals 0, phi2 equals 1. You calculate your number, you find 0 again. So another trivial one, okay, for the H. And I give you this example just for that you understand what phi1 and phi2 are. And then if you take just the occurrence of an empty vertex, which is exactly a defect, which are not supposed to be in the full impact configuration, in that case, you have 3 A's. And so and you calculate the weight this time, it's not 0, it's 3 A's, or 3A, again for the Hamiltonian. Okay, and maybe I have another one. No, that's finished. Okay, now I go back to KPZ. So how are we going to use it? So I showed it to you before, so just to recap. Remember the partition function of this system, of this type. Gamma of C is given by this KPZ formula. In our case, C was -2 for the dense case of the n equals 0 model, corresponding to kappa equal 2 for SLE, or kappa equal 8 for people like SLE beta. C equal -2, but we have a shift of +1, remember, because of this A term. So the central charge will be -1 here. And so if you put, now you go back to the original combinatorial problem, remember? It was just putting arches on a line. Remember, it was obtained by the partition function of single loop by cutting the loop. You cut at 2n minus 2n places. So it means the partition function is 2n. This is for the arches. 2n times the partition function of single loop on your sphere. And this one scales like 3 minus gamma minus 3. So and A, of course, the area is simply the area of is simply 2n, the number of sides. And so you get mu to the 2n to n to the 2 minus gamma. You calculate gamma of C minus 1, and it's given by this formula. That corresponds to the value we saw before in the original slide. So this is the way you do so simply by looking at the number of fields that you have an extra field phi1 in your fully packed case, and that gives an extra degree of freedom. C jump from -2 to -1, and that gives this non-trivial gamma. By the way, I am not aware of any problem in combinatorics of these types, which is able yet to produce exponents which are irrational. There is another well-known problem, meander problem, which has also been solved between quotes by this kind of approach a long time ago. And it has also a square root of some integer numbers. And that is also still an unsolved problem. This one is simpler somehow. The arches somehow looks a bit simpler than the meander problem. This is why these people looked at it originally, a long time ago. Okay, so yes, that is the one, yes. It will show back in the numerics. These are the numerics we did this time. And so you see this kind of convention. So n is increasing here to 25. So of course we went above to 34, but you have kind of slow convergence as there are all of these different colors are different types of massaging the series. So you get the numbers. This is, by the way, all of these numbers I showed you in the first column were exact numbers. They are obtained by transfer matrices. So transfer matrix, you look at your arches system, you cut the arches and you look at the propagation of one level of arches to the next level. So all of the numbers you get, they are exact numbers of configurations for finite sizes. And then you try to extrapolate what happens when n goes to infinity. And this is done by special ways of treating series, which are all labeled by this column without details. So you see that the mu square, remember the growth, the exponential growth factor is, converges well to this number. And then the gamma, the famous gamma, 2 minus gamma is 2.77, which is here. And that is given here by this convergence. So this is just a repeat was done a long time ago with better precision. So up to now, everything is fine. Okay, let's look at the correlation functions. So we look at various correlation functions. I'm going to go fast, which means, for instance, this one is the open line. So this is a way to look at the, remember, it was open line on the sphere, but now when you stretch it on with arches, you get something which are like here. So this was the open line on the sphere. This is, so there are different type of defects, okay, here. So we have a zoo of defects. I'm not going to detail them all, but they correspond each time. For instance, the first one, I showed it to you, remember? Maybe you remember? Was the first example I gave, 3/2 here and 1/2. So it corresponds to this system of arches. So you treat it with a transfer matrix approach. The same thing for this one. There are different type of defects. This is isolated. This is non-isolated. Yeah. And you have this one. So each time corresponds to different phi1, phi2. You see, phi1 here, phi2 here. Phi1, phi2. Just relative. Just fractional numbers. So these are different. So there is one with a defect, which is this one I showed to you before. This either not visited sites on the sphere, which corresponds to this sites here, and there are also these ones with again only a factors. All of these corresponds to phi2 equals 0 here, and all this stuff. So all of these were treated by transfer matrices. So in that case, and I show you the tableau here. So in that case, what was calculated from the exact enumerations up to a certain level of n, were these numbers. Okay, you won't understand it probably here, but essentially we computed these betas, which are either 2 minus gamma or combination of gamma with the quantum gravity exponents. So this one was A, the last one I showed. There was A, here you have 2A plus 1A, and then you have 3/2 of A plus 1/2. This one's the open line, remember? So you have this weight, and this one you have so it's all the defects we looked at. So these betas are the things which are calculated numerically from the exact enumeration of the configurations of these defects up to, say, n equals 25 or n equals 34. An extrapolation. But then, so we are going to see them numerically. But then you know that these guys, in principle, these deltas, all of these deltas here and here, they should correspond to the formula, the Physique formula for C equals -1. Okay? So which in that case, for C equals -1 is simply given by that formula. So it means if we have the H's, which we know because we know phi1, phi2, so we are able to calculate HM. We plug it in here, we should find the delta X. We put them back, we should predict the betas and check with the numerics. And that's where the surprise came in, because it was not working. And I'm going to show it to you.
When you say that you obtain that numerically, this is via this field theory approach?
No, this is not numerical. The field theory gives you the H. Oops. Oh my. I succeeded in
someone else.
I know. Ooh. I hope it goes away. Maybe I pushed the button too much.
I don't know how to remove it.
It goes.
Okay, someone remove it.
Oh, good. So anyway, so yeah, thank you for your question. No, this comes from the field theory approach in the plane, the Coulomb gas one, in the plane. There's a regular lattice, if you want. There's the hexagonal lattice in the continuum limit. So this one, we know all of these phi1, phi2 in the defects I showed you. So we put phi1, phi2, we get H. So this one we know for sure. The prediction, but we know them for sure. Now what we calculate numerically are the deltas. We calculate them via the beta, but that's the same thing because we know gamma. So we numerically evaluate the betas or the deltas, okay? The deltas which are here or here or here. Okay, in principle, we should know them. Of course, we should know them theoretically because we have KPZ. So we know the H, we put the H here, we predict the delta. So we predict the betas. So that was a prediction. And we said, well, we do the numerics and we are going to check. It's a nice work, easy to do and so on. But easy, not so easy. But anyway, you can do it. But the surprise was the fact that the numerics did not fit the prediction. So I'm going to come to that in a minute. Voilà, here they are. You see the betas are on the left with the error bars estimated. On the right, you have the prediction from KPZ via the H gotten from the field theory. And so you have all of these numbers with square root of 13 everywhere to the right. And you see the gamma, of course, beta Z was gamma. So that fits, the first one fits, but all the other ones, they don't fit. You say 199, 194, 190, 176, 119, 1. I mean, clearly there is a problem. That was a big surprise because we are strong believers in KPZ and Coulomb gas and so on. And of course, the numerics, they were done with, you know, high-powered computers, etc. So that was a question. So, and actually, we made something, an ansatz. We said, well, maybe something happened with the phi 1 term. It comes from the phi 1 term, all of this process. When there is no phi 1 term, no A terms, if you have no A vector, you will see everything fits. So we'll see that later. So we tried to repair. So that was really an approach. We have no idea whether it's correct or not. So what we did, still now, today, we don't know. So we tried to repair by enhancing the factor of the phi 1 term. Before it was 1, now we put alpha. And when we tried to move the alpha here, you see, from 1, which was the original prediction, to 2, let's say, by increasing the H. And then if you increase H, it means the delta by KPZ also increases. So you have this, and the betas also increase. So the betas move here, and so on. This one was correct, so no change. And if you increase, you see that you have your error bars. So you have a possibility to cross all the error bars, more or less, except for one, which is beta X. This one is not good. But all the other ones here, for 3, 4, so 4/3 here, for alpha called 4/3, they seem to fit. This one, here, they are in the error bars. So I said, well, maybe the real answer is to put 4/3. Okay. But then, of course, we try to guess what could be the general formula for any FPL model. So we came with an ansatz, but again, we don't know. And so if you do it for 4/3, by the way, if you try to do that, you are going to find that, you know, these are the numerics with transfer matrices. And here, these are the new numerics. And then you have this much better correspondence here between these. Okay? So it looked like, except for beta X. So it looked like beta X, which is here, is not so good. But for instance, this one is pretty good. This one is pretty good. This one too. So this was an ansatz. As I said, we are not sure. We have a general formula, and for any n, and we have some checks because in some cases we know the enhancing. So anyway, you don't need that. So it's no longer G prime equal G like we originally did. It's G prime equal alpha of G. And this G prime, we found the formula in general. In terms of kappa, there is correspondence in SLE. So I skip it because I don't have much time. But as I said, it's purely, it's an ansatz, and we are not even sure it's correct. Of course, this formula somehow says something which we understand, but we don't know. So it means, anyway, the message that for some exponents, at least for some kind of defects, KPZ has to be repaired some way. Okay? So and we'll come to that later. So what we did after, this is some kind of geometrical illustration of the formula, but I skip it. So in the last 10 minutes, I'm going to use to say the content of the second work, because we tried to understand, you know, what was going on. So we looked at more complex cases. It means we looked at the cases where you take, you know, more general bicolor maps. So it means in that case, for instance, these are maps made with vertices which have, you know, connectivity. In that case, five regulars. So there are maps where the vertices, instead of being trivalent, random planar maps, they are 5 valent. Okay? So we call them regular. We also did, so of course, this is the the arch version, but again, if you put yourself on a sphere, there is a single Hamiltonian cycle filling all your sphere, random sphere, and the sphere is made of 5 valent vertices. You can also mix. You can mix, 3 valent with 4 valent. This is a 4 valent vertex, 3 valent. Again, bipartite, bicolor. And then there is the case which we call rigid. It means when you traverse a vertex, you leave as many empty edges here as empty edges to the left and or to the top and to the bottom. So it means you go when you enter a vertex, you go straight and you split everything equal to your left and to your right. Okay? So these are the regular rigid cases. For Q equal 4, it means you leave 3 on the top and 3 on the bottom. And in total, you have 8. So you have 8 edges. And these are the cases actually for people who have followed the literature. Looked at this case for Q equal 2 was a case looked at by Borga, Green-Sun, and Borga, Green, and Park in their papers some years ago. So they looked at the rigid case. So we have all of this zoo of possibilities. We studied them with transfer matrix again. And we also did some theory of it. And seems to be missing something. Ah, yes. Voilà, here. So these are the first observation is that, so there is a theory which, is rigorous behind it. You can show first that when your lattice is regular, means before it was 3 valent, 4 valent, 5 valent, and so on. When it is regular, all the central charge is shifted by 1, so you find the same gamma as before. Okay? But if you mix vertices, or if you make them rigid, you can show that actually you have no A component. You remember the famous A component, the one which actually caused problems? This one is frozen, or is not there, or is frozen. So it means there is no field A, no phi1 field. You are back to the dense phase. In that case, you have the central charge of the dense polymers, which is -2. And then the gamma corresponds to -1. So, and these are the numerics for mixed case, for instance, here. And you do find the gamma equal -1. But if you take all of this, we looked at all of these regular ones, we did find again the gamma as before. This was a check of the theory. You can look at what happens if you mix or don't mix or makes it rigid, and that changes things. So that is well understood. And then we looked at something else, which was the long distance properties of contacts. This is an illustration. So you imagine that you have lattice on the sphere, regular lattice, and you have a cycle, which is, you have a single cycle, right? Hamiltonian cycle. You paint it, half of it green, then half of it red. And then you look at the places where the red and the green come into contact, okay, on your lattice. So, which is illustrated here. Of course, you do feel the lattice, so it's like here too. And then there is a certain rift, rift in between the two, and you have a certain path circulating between the green and the red. Of course, if you think it, so I'm not in the random setting, I'm not in the quantum gravity setting. I'm on the lattice, meaning in the scaling limits that should be SLEs. Remember, we are in the fully packed case, so it means that the SLEs which are behind this are SL8 for the green and the red part, because you feel the lattice, so it's a piano curve. So it's SLE8. So I symbolically represented by the union of the two curves, C1, C2 are the red and green curves. The union is SLE8, all of this set. But then the intersection, the contact line, is of course the dual of SLE8, meaning SLE2. Okay? So it corresponds, so this dotted line here should be an SLE2. And the SLE2, we know the other dimensions is 5 source. So we are in the plane, so it means the intersection of the two, right? Symbolically, C1 inter C2, this expectation of the length of the path should be the area times 2 to the power d tilde, the other dimension divided by 2, okay, because that's an area. So it means, so in terms of h exponents, the Hausdorff dimension here divided by 2 is always 1 minus h. So if you know delta tilde here, d tilde, you know H. The famous H we put in the Capizzi formula, right? So in that case, this is 5/4, and so H is 3/8. So it means the scaling dimension of a point, a path here sitting in between the green and the red one, should be an SLE2 with a scaling dimension 3/8, which is a two-leg SLE2 for people who know this multi-legged spontaneous SLE. So we have 3/8, and this is valid, of course, when you have a large area. So now I'm going to use this one in the Capizzi formula. Remember, because this is an H, so I can put it in the Capizzi formula, which is next slide. And so this is a kind of last slide with formulae. Remember, you have gamma. So either C equal -2 or C equal -1. So for people who like Liouville quantum gravity, like the exponential of gamma times the free field, the famous gamma, the Liouville gamma, in that case is square root of 2, square root of kappa equal 2. Okay, that's gamma equals square root of kappa, which you have in LQG. And in the case of C equal -1, it's more complex. The Liouville parameter is greater. This gamma is not the gamma we had in the partition function. The Liouville parameter you put in front of the Gaussian free field to describe the fluctuations of the random measure on your parameter. So this is just for people who know LQG. But anyway, forget this, but these two cases. But remember, in Liouville quantum gravity, the scaling of the length of the path here, this dotted line, should be the area to the nu, as this nu is 1 minus delta. Again, before it was 1 minus h in the plane, in the regular plane, in the Euclidean setting. When you're in quantum gravity, it's 1 minus delta instead of 1 minus h. The a is just the position of the point, and minus delta is the cost of putting a defect. Okay, so Capizzi, well, that's easy. You remember we have C equal -2. You take your Capizzi formula, you put 3/8. Remember, 3/8 was h. Remember, it was my 3/8 here is the formula we had before. This one here. Okay, we put this one. And we take two cases. First case, C equal -2, then you get delta equal 1/2, very simple. 1 minus delta is 1/2, so it means this new exponent is 1/2. Second case, C equal -1, okay, which is the case when you have, the regular 4-leg or 5-leg lattices, remember, or 3-leg lattices, the non-mixed or non-rigid case, the standard one we started with, C equal -1, then you find this delta to be, for 3/8, being quite different of this type, or a new 1 minus delta given by this formula. If you do the numerics, you find 0.483715. So this is a prediction of Capizzi, okay? For C equal -1. Prediction for Capizzi is C equal -2, 1/2. So clear this is distinguishable. And we looked at the numerics. They are here. So remember, we knew that when you are rigid, it's C equal -2. So it's 4 regular, but rigid. So it means you cross and you split things to your left and your right equally. Then you have your prediction is, it's not easy to find it. So you see all of these conversions of data. But there was a trick which we discovered, which allows this very fast convergence to C equal to nu equal 1/2. So that corresponds to what we knew. C equal -2, nu equal 1/2, remember? That's a prediction Capizzi. We looked at the case where you have mixed valencies. When you mix things against C equal -2, you destroy or you freeze the A component. So you don't have this famous A component. So 1/2, again, you do find this very good convergence to 1/2 here. But if you do the regular case, just the one we started with, 3 regular bicolor, the trivial case I started with in the talk, well, you have the same kind of good convergence, and you do find this is the line of this famous 0.437, with this correct of 13 and of 11, if I remember correctly. So you do find it fits with the prediction. So it means, at least for this story of contacts, the Capizzi prediction works even in the C equal -1 case, right? So it did not work for all of these exponents we had before because there were A components in it. In this case, there is no A component. So see, somehow is the story that when you have this special defect, this A part, then KPZ is in trouble. But when you have no A part, then KPZ is not in trouble and does well. It was not easy to find 48, actually. It was, at first, we found 0.52, sorry. KPZ looked wrong, but finally, we got it, and we could pin it. So KPZ works at least in half of the cases. So this is to answer your question as before. What happens for other lattices? And that's where there is a big surprise, because here I showed you, there is no quantum gravity here. It's no longer on the random planar map. These are the results of these people in the old days. I forgot to say it, but there was this work by Jacobsen and other people where they looked at not only at the hexagonal lattice, but at the square lattice. And they were able to devise the field theory, the Coulomb gas, for the square lattice. It was different from the one I showed you for the hexagonal lattice. And they did calculate the exponents of multi-lines. Multi-lines, you remember, for SLE, it means you look at several SLEs starting with one point and finishing somewhere else, right? The multiple SLEs problems. So the number of lines here, I call it L, little l, which is in this formula. You see L here. So this is a formula. If you take SLE, you take a certain number of paths sticking out of a point, okay, mutually avoiding, multiple SLEs, LSLEs, they are going to have a certain conformal weight, H sub L, as the number of lines, given by kappa, of course, the kappa of the SLE, and this famous quadratic formula, which corresponds to the Coulomb gas of Linus a long time ago. We knew how to calculate this in the 80s. Anyway, so this is the general formula. So multiple SLEs are also called arm exponents for SLE. Now, suppose you take the fully packed problem, not the dense problem, the fully packed problem for n, any n of the fugacity of your system. When you have an even number of lines, little l equal to 2 kappa, this is 2k, it's not kappa, 2k, then it is the same formula as the SLE one. So it means the fully packed doesn't distinguish from the dense ON model. And this is where you don't have economy. But if you take the odd number of lines, so little l equal to 2 kappa, 2k minus 1, then you have the formula for SLE, which is this one, plus 3 over 4 kappa, which is a shift you get, but this corresponds to the hexagonal lattice. But the work was done also for the square lattice here by these other people. And then they found that the shift from the SLE formula, at the time there was no SLE yet, so it was the Coulomb gas formula of the ON model. The shift was given, I rewrote everything in terms of kappa, but at that time it was written in terms of G, and then it is 1 over 6 plus kappa. So it means, and this is a real mystery, and this is a case where actually KPZ will not work, because this is when you have this A component coming in. Okay? So we know already that we checked, by the way, we compared to this formula, this type of formula before. It was not working. If you compare with this type of formula, it doesn't make it better. Right? But the fact here there is no quantum gravity, no KPZ. It's just the predictions of the regular lattice approximations. In the continuum, you are supposed to see exponents, and they do depend, at least for the odd number of lines, which correspond to the presence of the A term in the field description. They correspond to different predictions for the two different lattices. So it means there is a memory of the lattice, even so you are in the continuum. And this is kind of unheard of for a non-universality between quotes, which is unheard of for SLE. Okay? And this for sure, believe me, these predictions are probably correct because they also checked it numerically. So, and the idea, so of course here just the recap was this 3.8 we had before corresponds to the fully packed loop n equals 0 model with 4 lines, but it was just the same as the SLE for kappa equal 8, or the dual one, the SLE2 for L equal 2, which was these dotted lines, but the dotted lines were switched between 4 lines of the dense case. So this is just, it means that when you remember for the contact between green and red, KPZ worked. It worked because it was a case where you had an even number. And that fits with the formula we have. So returning to this difference between the lattices, it comes from the fact that somehow, even though you no longer see the lattice, the fact that you are fully packed, that you have to follow the lattice, at each side, you have to fill all the lattice, somehow it keeps the memory of the kind of lattice you are in. So these are the two examples we know of. There are many other lattices, I don't know what was the answer. So it's kind of mystery for people who are interested in scaling limit of SLEs and universality. And again, this is exactly where also KPZ doesn't work. But somehow, for the same reason, because when you do KPZ, the key ingredient of the proof of KPZ is the fact that the Gaussian free field, which represents the fluctuations of your metric or the fluctuations of your measure in quantum gravity, the Liouville measure, is decoupled, independent of the fluctuations of your SLE, of your system of paths. So there is a decoupling, they are independent. And that creates KPZ. When you insist of being coupled in such a way that you always feel the lattice, even the random lattice, somehow you create a certain kind of coupling between your path and your random lattice. Right? And in that case, KPZ clearly no longer works. We try to repair it. Perhaps it's true, maybe not, we don't know. But clearly there is something happening there because of this coupling. But you see this coupling between the path and the lattice, even when you are in the regular case, the coupling between being square lattice or being an hexagonal lattice, there is something which remains in the memory of this. Okay, and with this, I finish.
Thank you. Are there any questions also from people on Zoom? Maybe I can start with a question. So the 3/4 that you see there in the second line, was it the same alpha that you had to add as a correction?
No.
There is no relation between
it. No, but it would give this. I mean, the alpha we put would give this. Good question. Yes, I think yes, I think so. I forgot. Okay. That's a good question. I will double check. Thank you. Okay. Yeah, I think so, but I have to do. Yeah, I think so.
And for the other model that you were, when you changed the lattice and you were adding more arrows,
yes.
Did you also check how you should correct APT when you have this A?
No, it was too difficult to do.
Okay.
It was too difficult to do with the transfer matrix.
At the level of the numerics.
Yeah. Yes. We are limited in the abilities. Otherwise, we would like to look at different exponents and so on. But in a way, I think we understood the essence of the problem. It's a coupling of the A with the lattice. Yeah. No, nobody will do. We cannot do. Yes.
And did you study the case with the rigid case with mixed valency?
No. But they will reinforce each other because both give equal -2. So I don't think we'll have a surprise.
Any question? I don't know if you see something on the chat. No? Okay. So let's thank the speaker again. And there will be a coffee break now in the other room, and then we resume at the post.